All right, hello, so my name is Mo, and I'm going to be talking about this idea I've been tinkering with called neural spatial curves, but really it's going to be about autoencoders and TensorFlow. So what we're going to do is talk about space-filling curves, what an autoencoder is for those that don't know, what neural spatial curves are, and also some of the improvements I went from my initial just kind of like a DeepSeek R1 sketch of the model I wanted. So space-filling curves, for those that are not in the know, are math functions that map one dimension onto n dimensions. Whoa. So basically what it does is it takes this variable that has kind of like 1 degree of freedom and compresses all of the values in that variable into 2 degrees of freedom. I'll show you what that looks like in a sec, but this is used in a lot of fractal related math. So probably the most popular one that I'm aware of is Hilbert curves. So for a Hilbert curve, you define a certain degree of fidelity that you want for your space-filling curve, and then for any continuous n, it'll output a continuous x and y coordinate. So in here, you can see it kind of starts here, it zooms through everything and then outputs. So anywhere on here, this is from the value 0 to the value 1, we can get a point in space. And if we want finer and finer grained fidelity, we increase kind of the complexity of this little grid. However, this requires a bunch of math. And, you know, math requires being super smart and really like dutiful, and I'm really lazy. So I was like, what if instead I could do a neural network that can basically figure this out for me using magic? And the main thing is I just wanted to have a small model that does something that I can do incremental improvements with to kind of like also be able to see visually what the model is thinking and also just build my intuition around training. So autoencoders, this is very common. This is what I kind of decided to train my model. Basically, you take some sort of input, you encode it into a latent space, then you decode that back into the same input. And what happens is you're training the neural network to compress some amount of data into this latent space and back out. So in my case, I took the x and y positions, I encoded them into a dense layer of 64 neurons, had a latent space of 1 neuron, and then decoded back out to 64 and back out to x and y positions. So basically I just slop dev'd this where I had the AI spit out kind of like Python code for the description. This is it, it kind of works. So the next step I wanted to do is actually get a sense of, is it actually encoding or decoding? Like what is the actual fidelity? So over here, the purple points are the points that I tried to get it to predict, and the green points are the ones it actually predicted. So these white dotted lines are kind of the loss or how inaccurate the model is. And so what we can see with this simple model is it's encoded this little S shape into that single neuron in the middle. And so all XY positions are encoded into some value, and then that value is split back out into this larger space. So the next thing I did was I looked at the code and I'm like, oh, maybe I'll like mess with activation functions, maybe that'll do it. And so I was looking at ReLU activation functions. I'm like, oh, they'll make it more nonlinear, and nonlinear is good. And I completely screwed it up. So as you can see here, everything outputs 0, 0, so not good. What I learned from this is in autoencoders, it's good to have some linear layers at the end layer, and in my case, right before the latent space. Then I was like, okay, what if I add more hidden layers? I add in an extra layer to the encoder and decoder. Now I'm getting a more interesting like ninja star shape. Then I was like, okay, what if I try throwing more data in the training, have a larger batch size? Now we're getting this more complex S curve. And so every time we increase the complexity of the curve, there's more of the space that's being filled, and we're getting more and more accuracy on the points. So next I added batch normalization. So by default, I was just kind of like throwing the raw data in there, throwing random values, and then kind of shaking it to hope that it would come up with a good curve. But what I did instead was, before each activation function, I added a batch normalization step, which kind of takes all of those values and performs a normal distribution on it. So then there's less kind of like wild fluctuation, and it makes training more predictable and generally better. And as we can see, this is starting to look a bit more like a Hilbert curve, where we have like a low order kind of like weird curve through space. Then I was like, what if I just throw more neurons at it? And I basically increased every layer by 2. We're getting, again, more complex looking internal representation. And then I was talking to Quen 2.5 coder, 3B, and it was like, you should totally add a dropout layer. And I was like, great, I'll add a dropout layer. And dropout layers, what they do is they set a random subset of neurons to 1. This can help with avoiding overfitting, and it's not useful for this particular case because it just completely killed my curve. It became this little like omega shape, not very nice. Then I was like, okay, scratch that. We're gonna add more layers. And so I added a third hidden layer. And now it's getting like even more complicated. And then I was like, okay, what if I throw more neurons at it? And I doubled all the neurons, and it became even more complicated. And I also played a little bit with different loss functions, or loss functions. So mean absolute error is, oh wait, I forgot my notes. But it's a little bit better when you have kind of large fluctuation in your data. And the defaults that I was using was mean squared error, which penalizes outliers a lot, and it kind of like makes your model more predictable. Whole other talk for that. Then I was like, okay, I keep plateauing in my learning rate really fast. What can I do to kind of improve that? So I found this built-in function in TensorFlow, reduce learning rate on plateau. And what it does is, whenever it's seeing that the learning rate is kind of like plateauing, or just kind of jumping between 2 values, it slightly reduces it some number of steps. And so this kind of helps the gradient traversal in the learning just be a little more smooth. So then afterwards, I also just trained it for way more. At this point, my small model was taking like 30 minutes to train every time I made a little change. And I decided, you know what, this is my final spatial curve. So this is completely learned by just jiggling some numbers around in a big matrix. And you know what, it's not as good as a Hilbert curve, but along the way, I learned some conclusions. The least complex model with the little S shape was actually like good enough for some cases. Like I could pretty much cover the entire space with like 20% or like 80% accuracy or something. It wasn't like that bad given the space I was covering. As well, the biggest effect was having more layers and more neurons. So, you know, like deep learning is good, who knew? And then the batch normalization really helps stabilize the training a bit. And the linear activation thing, now I know, I'm probably gonna play with more activation functions in the future, but when I start using this for like a real model with signal processing that I'm planning to do, hopefully that'll still be true. Yeah, so that was my,
You said it takes a lot of math to do it computationally, not using a neural network. I'm curious, if you were to code it to do it that way, would it be really, really slow, or would it be faster than this, or somewhere in the middle?
yeah, so by a lot of math, I just meant like there is an equation with a bunch of math on it. It's actually really, really fast. Hilbert curves are like probably many orders of magnitudes faster than doing this neural network. It was more like I didn't want to have to like think about the math at all and literally just throw a model together, see if it could figure something out good enough. But if you're actually wanting to do a space filling curve, like like actual space filling curves will be way better than anything a model will come up with on its own. Yes.
You tried conditional variation of autoencoders, but I think the architecture might be the fusion model in itself, because introducing noise will make like help you get your target data easily than autoencoders, because autoencoders or maybe Gaussian approach might be easier, because you need to somehow predict where the points are, and you're trying to get closer to it. While autoencoders are more like they don't know what to do in the latent space because they're going back. And most of the things you try to like dropout and ReLU, it's mostly helpful for overfitting, but your problem was mostly under. So I think
Yeah.
the architectural change and introducing gradient and
Yeah.
we can talk more.
Absolutely, would love to talk more. One other thing that I started working on but didn't include in this was sparse autoencoders, where I was trying to get it to like really make use of that latent space more, or just like each individual layer. And that was like a big loss function with a bunch of math, and I was reading through the blog posts and it didn't make it in time, but definitely this is not the best way to do it. It was more like, here is some stuff I found, but I would love to talk more. Any other thoughts? Yes.
So it compresses it down to this one-dimensional latent space, and that's
Yeah.
kind of like the green S dots. I'm a little surprised that, because the purple dots were just randomly distributed, right?
Yes.
So I'm surprised that it didn't overfit more, where it was kind of more discontinuous, where the green dots were a lot closer to the purple ones. Because you had a lot of parameters, it should be able to fit that for, like, you have less than 10,000 dots there.
So these dots I generated after the model. So these are not the dots that it was trained on. I generated, I think it was 100K random positions. And then I was training that in batches of, I think, 256 or 300 epochs? I
Yeah.
can't speak English. So overfitting on the particular training data didn't seem to be an issue. But also, yeah, I didn't fit the 10,000 points in the space.
Did you enjoy using TensorFlow? Was it fun?
So I had a lot of fun until I tried to do GPU acceleration on AMD. And then I had a lot of not fun for a while. And then I was like, you know what, whatever, screw this. My CPU, I have enough cores, I have enough speed. And I got to a point where the CPU was drawing so much power that training, that my battery was going down even though I was plugged into the mains. So other than that, it was pretty fun. Also, it was fun co-creating with just like really stupid model. Like Quine 2.5 Coder 3B, very, very smart for a 3B model, but like some of the things that it rambles about is just like, why did I even try?
And was there an architecture that would have made the AMD GPU acceleration work, like if you switched to PyTorch or some other thing, or was it just like not gonna happen at all?
So my particular issue is, since I have a really weird computer, the AMD ROCm drivers are just not great, and also instead of running stuff inside a big Docker container and all these layers of abstraction, I tried to install ROCm directly in Arch, and TensorFlow has a bunch of like ROCm dependency paths hard-coded instead of stuff being properly packaged, and it's more dependency hell than anything else. So like, it can be addressed if you kind of like bend yourself, and I just wanted to make the thing go. So in the future, probably I'll use a Docker container and all that stuff, but CPU's fine, you know, for small models, it's enough.
One more question?
Sorry, so just kind of going back, I don't think I fully understood like the problem setup here. The goal is to constrain the embedding so that the embedding is producing the XY coordinates?
Yeah.
So why not have like a loss, like why choose an autoencoder maybe, but also you could kind of have like a constraining loss on the, because you know the XY coordinates anyway, you know what embedding you're trying to get at. You could maybe put like a constraint loss on the embedding so that it's actually reproducing the actual XY coordinates.
I don't know how to do that yet. The thing was, I wanted to have this like nice separation between the encoder and decoder, and I wanted to be able to look through that single neuron in between the two and just see what sort of value can I get if I map from everything from -1 to 1 and be like, what is that value actually trying to encode if I use just the decoder part. I actually wrote a bunch of code for that I didn't include in the slides. But I wanted to see like visually what it was learning. As for like setting up the loss, I just use the defaults, so that's why it's not very fancy. But I would love links to better ways to set up the loss.
Yeah, maybe I'm misunderstanding like the problem setup. I don't think I fully got like what the goal of the whole experiment was, but yeah, maybe you can talk to it.
Yeah, the goal was just to take these two values and compress them in one value and then decompress that back into two values.
But the value you're trying to compress it to, it has like a space already defined, like you're trying to project it into like on a Hilbert curve, right?
No, the Hilbert curve that was like just for
Okay.
visualization what a Hilbert curve looks like.
Okay.
This is not actually doing a Hilbert curve. It's doing it's actually not even using that full neuron. In fact, I found in my testing, it was only using ranges between like 0 and like 0.3. And then on either side of that, it was just stretching it into infinity. So, yeah. But, yeah.